Hello and welcome to my next tutorial about PrePoMax. This time I will show you how to analyze a thin-walled capped cylindrical pressure vessel meshed with shell elements. I will create a new model first, select a unit system, and now I have to import the geometry. I will use the step file format again. Here you can notice that I modeled only the mid-surface of the pressure vessel, and that's because of the way we define shell elements. What's more, the model represents only 1/8 of the whole structure, and that's due to the use of symmetry. I will show you how this model was prepared in FreeCAD. I will also open the sketch so you can recreate this geometry if you want. Here are all the necessary dimensions, and the sketch was revolved using 90 degrees. Let's go back to PrePoMax, and now I will create a mesh. I have to specify meshing parameters. I will use 10 millimeters for maximum element size, and I will choose quad dominated mesh because we can use quadrilateral elements for shells. Let's confirm this and generate a mesh. The mesh is already generated, so I can proceed to the analysis setup. Let's start from material definition. I will define steel material, and I will provide Young's modulus and Poisson's ratio using the values that we know from the previous tutorials. Those are the typical values. And let's create a section now. And what's different is that in previous tutorials we used only solid section, while in this case we have to use shell section because we mesh this with shell elements. And in addition to the material specification, I have to provide thickness. This will be 20 millimeters for this particular pressure vessel. I don't have to use offset, so I'll just specify the thickness here. And I have to select those two regions because they are separated for the definition of this section. Let's confirm this, and now I can create a new analysis step. This will be static step with default settings. We won't use any form of nonlinearity, so this will be turned off, and the rest will be set to default. Let's confirm this and define boundary conditions and loads. When it comes to boundary conditions, as I said, we utilize symmetry, so we have to apply symmetry boundary conditions. There are no predefined BCs like that, so I have to define them manually using displacement rotation boundary condition with constraint on proper degrees of freedom. Let's start from the symmetry in x direction. I will call this sim x. And let's pick this edge here and this one here for this constraint, and I will constrain the translation in x direction as well as those two rotations here. Now I can confirm this and create a new boundary condition of the same type. This will be called sim y for symmetry in y direction. I will pick this edge right here, and I have to constrain the translation in y direction as well as those two rotations right here. And now, instead of confirming this and going back to the model tree, I can just click OK and new, and this will let me create a new boundary condition without leaving this window. Let's define last boundary condition. This will be sim z, and it will be applied to those two edges right here, this one and this one, and I will constrain the translation in this direction as well as those two rotations right here. Because I should have mentioned that before, the shell elements, unlike solids, have rotational degrees of freedom. Let's confirm this, and now I can proceed to the load definition. I will define pressure load, and when it comes to the value, here you can see that we use 5 megapascals. Here are the analytical results. We'll go back to this later. So let's define pressure, 5 megapascals acting on those two faces. This will be internal pressure, and now you can see the whole model is prepared for the analysis. Now I can submit this analysis. Thanks to the use of shell elements and symmetry, it shouldn't take too long to get the results. In fact, they should be available soon. Yes, they are already available. Let's open them. And here you can see the distribution of displacements and stresses. You may also notice that shell elements were automatically expanded to solids, and this happens for both calculation and visualization in CalculiX. I can turn the deformation on because it's currently off. I can use the default automatic setting, but for now let's switch this back off. Here you can see the stress distribution. Let's compare this with analytical value. Here's the analytical value of von Mises stress in this pressure vessel, and I will use the query tool to check the stresses in various locations of this pressure vessel. Let's check this also here. Here in various places, this is used to query selected nodes. We used this tool before in previous tutorials. And you can see that the agreement with analytical results is quite good. But let's also take a look at displacement in the x direction. I can also query this using this tool. Let's check this here for several locations, and I can compare this with the analytical value. Since we confirmed the correctness of the results, I just want to show you one more thing. You can use the results transformation option and apply symmetry in all the available x's, and this will make the results look like we have calculated a whole pressure vessel, not just a piece of it. And while in fact the analysis was performed using 1/8 of the whole structure, but for the visualization purpose we can apply transformation to achieve such an effect. That's it for this PrePoMax tutorial. Thank you very much for your attention. As always, feel free to ask any questions and suggest topics for future tutorials in the comments. Have a nice day and see you in the next video.